It's a great pleasure to have my former brilliant student, Dr. Tewodros Amdeberhan from Tulane University, speak about a journey with MacMahon and Ramanujan series. As usual, please mute yourself unless you have something to say.
Okay, thank you, Doron, and nice to get connected on Zoom, although we have been on email together, and we wrote a couple of papers recently with Doron too. Again, I kept being lucky. So I want to share with you other lucky situations as well. Here, why I call it journey is because there was some research we started a couple of years ago, but which actually triggered other research, and it kept continuing. Actually, it's branched out very well. That's why I want to share this with you instead of one single paper. Okay, so we'll start with some nomenclature. Here is the first item that you see on the left is the Q analog of the integer x. And then on the right, you see Q binomials or Gaussian polynomials. And later on, we might have a chance to look at this notation, either as an infinite product of the Q's on the right-hand side or as a Dedekind eta function. Here are examples. Everything that you see here, whether it is the Q analog of integers or the Gaussian polynomial, Q binomials, they're all polynomials. All right, the story begins about this journey as follows. A year or two ago, actually we started working on this one 2 years ago, although it was published in 24, with George Andrus and Roberto Taurasso from Italy. What I'd like you to focus on is not the last two, but look at the first one. These are, think of it like the bottom one is K1 squared in the denominator of the first line, and the second one is K2 squared, KT squared. These are the Q analog of those. And then in this work with George and Roberto, we were able to find two other representation of this sum. I like to emphasize that this is a finite sum, although it's a multiple sum, but all the entries cannot exceed n, therefore it is a finite sum. But it had found different writings. The middle one, for instance, expand the sum twice, doubles the sum, so you have 2t instead of t of them, and then it breaks up the even and the odd indices, as you can see. And the last one is desirable, as you will soon witness, because it turns into a multi-sum into a single sum. That's the merit of the last equation. Now, of course, we take the limit as n goes to infinity, and then from the previous triples identity here, triple equations, we only, for the purpose of our current discussion, I'll take only the first line and the last line. If I do, then this has become now an infinite sum, which means K1 up to KT, all these are t-fold integers, but they can go up to infinity. And then for notational simplicity, I use the product, and I dissolved this in Q notation, and I wrote it in this way, so that's more visible. The right-hand side is still a single sum, but of course, an infinite sum. This is important for the foregoing discussion. So you might wonder how we prove this. We prove this using Q-series manipulation. On the other hand, while we were working on these things, George Andrews actually recalled something that he has done from the past. And this is a series, infinite series representation, again, is of the same kind. And the only thing you have to take away from here is you don't need to remember the right-hand side, but the left-hand sides are very similar. Here, the integers k1 up to kt are strictly increasing, but earlier we had weakly increasing. Okay, that's only. So he realized that this is something that he has done with Simon Rose, and we want to see if there is anything we can connect with that kind of research. So as it turns out, to explain this, I need the notion of the partition function. I'm sure most of all of you know, but I will say it anyway. A partition is a weakly decreasing sequence, and they add up. It adds up to n in this case, and the notation is lambda of n. Here are examples of a partition of 5, and the ones highlighted in red will be relevant for the next couple of slides. Notice that the ones I put in red are partitions in which all parts are equal. And this is a Young diagram representation of partitions. While I'm at it, please look at the example, especially called the frequency notation. It means 1 appears once, 2 appears once, 3 appears twice, 4 appears none once. We will use that notation. Okay, what we notice is the following. Here is a kindergarten fact that you all know. It connects the world of addition to the world of multiplication. That is, partition being additions, divisors being multiplications, then the number of divisors of an integer is exactly equal to the number of partition of n, but into all parts equal. So this will be important because it has to do with what George recalled, and this is going to be due to MacMahon, the famous MacMahon, that Doron likes as well. And what MacMahon did was, instead of taking two numbers multiplying to n, he took t-fold of them. So assume that you decide to partition n using t numbers that you call s1 up to st, all of them distinct, and the mi's are their frequencies. They appear so many times. So it's like blocks after blocks of partitions. Then this sum is the MacMahon partition function. So it depends on how many parts you want, and it depends on what number you want to partition. And this, the remark is just what I said. The last line is a reminder that when t is 1, you get the usual sum of divisors. At the same time, on the left at the bottom, I wrote down sum of divisors into any power nu. Okay, this will be connected to what I said earlier. So if you look back into this highlighted expressions, the ones in red and blue, these are the ones that we worked out with George and Roberto, but this is what George and Simon did. Now we write a generating function for them, and this is actually the generating function for them. And this will be a generating function for the quantity I just defined, and that we call MacMahon partition function. So these numerical values are captured by this multisum, t-fold multisum. And this is from MacMahon, and this is from us. just to remind you, the three identities that I showed you much earlier is actually something that has to do with this infinite sum, t-fold infinite sum. So now, okay, they look very similar, of course. What's the connection and what can we do with them? What we want to do, what we want to observe is, first of all, when t is equal to 1, both family of infinite series boil down to the sum of divisors. So to do more on them, we want to introduce, recall or introduce the so-called certain quasi-modular forms, the Eisenstein series E2, E4, E6. You don't have to remember much, just that they are made up of sum of divisors, powers of sum of divisors. 1 power, 3rd power, 5th power. Then the monomials made up of these three, if you raise it to powers alpha, beta, gamma, respectively, then it will be considered as a quasi-modular form of weight 2 alpha, 4 beta, 6 gamma. And then this will be the generators for the ring, the graded ring of quasi-modular forms. So the three of them together, they form a quasi-modular ring. And if you only work with E4 and E6 instead, then you have modular forms. E2 fails to be so. But on the other hand, in our discussion today, we will also get a chance to talk about using all of them, the even indices E4, all the Eisenstein series, E2, E4, E6, E8, and up to E10 forever after. And although I didn't write them all on this slide, they have a similar structure. Okay, so now back to George and Simon. They showed that the MacMahon infinite series, multi-infinite series, is a quasi-modular form, mixed weight. That means it involves all weights up to 2t, okay, over the congruence group SL to Z. Now, of course, it turns out that it was good news that the other allied Q series that we introduced at the beginning, which is mimicking what MacMahon did, they are also of the same structure. They are quasi-modular and their weights does not exceed 2t. Well, how do we prove that? Since George and Simon proved the first one, then as it turns out, we got lucky. We can prove the second one fairly easily, which is because of the duality between the elementary symmetric functions and the complete homogeneous symmetric functions. They are related by this convolution identity, in which the xi's, this is the ei's and the t's, the homogeneous functions, complete homogeneous symmetric functions, they are all functions of infinitely many variables, and the variables are of that structure with a Q expression. So that takes care of proving our theorem based on George and Simon's theorem. That's nice, but to make it more interesting, what Simon and George did was they were able to theoretically prove that this UT, MacMahon sum, is quasi-modular, which means it's a polynomial with monomials E2, E4, E6 without telling you what the coefficients are in the linear combination, So here is what we did. Later on, this time switching co-authors to Ken Ono and Ajit Singh, we actually were able to find explicit coefficients so that we can tell you what the coefficients are. And these are the coefficients. WA has a closed form, W has a closed form, but the CI's they depend on three parameters, so they are expressed recursively. This is where I cherish the fact that I was a student of Doron, an experimentalist at heart, so that helped create this formula.
So you found it experimentally first before proving it rigorously?
Definitely, because
Wow.
nobody had any set of data for these numbers.
Wow, really. So,
Yeah.
so you first crank out this coefficient C of alpha, beta, gamma, and then you try to guess this recurrence?
Yes.
Wow.
Yes.
Very
It was an effort, especially W proved to be a little bit challenging because it's not obvious.
Wow, it's really impressive.
Yeah. And then, And then this is about MacMahon's sum, but what about the allied series that we worked on? Again, with Ono and Singh, we were able to find this expression. But I want to mention something. In here, we wrote this as a quasi-modular forms using E2, E4, E6, the fundamental generators. However, the new infinite multi-sum UT, by the way, UT as well as UT star, they can be viewed as multi zeta functions. But that's not important for us now. So this time, though, here is the expression we have found. It's a closed form, but in terms of Bernoulli numbers, and they involve, however, E2, E4, E6, E8, and all of them as needed. The higher the weight, the more you need of them. And this is a generating function. This is an expansion in terms of Eisenstein series. This again is experimental first. Here are examples of the two types. As you can see, the first one relies heavily on E2, E4, E6. For instance, in the second one, if you have E8, it's possible theoretically, but later on we'll have explicit things, theoretically to express E8, the Eisenstein E8 in terms of E4, because E8 is E4 squared, so it degrades down. But in this case, we're not going down. We use all of them. All right, the next character is another famous mathematician, Ramanujan, and he does anticipate a lot. You will see in a minute. This is what he wrote in some of the things he wrote in his lost notebook. And as you can see very clearly, it's very readable. And he wrote stuff that's unreadable. Let's make it readable. Okay, what does he say? He wrote this quotient of theta functions, if you like to say, but let's say infinite series. And notice the index is even in both of them. So he wrote this 2, that means for any positive t. Then he expressed each one of them in terms of what we call now E2, E4, E6, Eisenstein, but in his days, he called them also PQR in the literature. So he wrote a few of them. And then he followed through by saying that actually all of these guys can be expressed in terms of the Eisenstein series. Of course, he didn't spell out the coefficients. He said that they can be expressed this way. So it means in modern language, this means both UT and Vt are quasi-modular forms. That's what he is saying for any t. And I want to remind the audience that these functions, this quotient of theta functions, are different from the MacMahon multi-sum series and our multi-sum series. This is a new discussion. So still, we're expecting them to be quasi-modular because Ramanujan claimed it. And actually,
sorry, Tewodros, remind us what does quasi-modular mean, and also what does modular mean?
Modular means it respects some transformation rules over matrix action on a set on the complex plane. It's a bit of an explanation to do modular forms.
And quasi-modular forms?
Quasi-modular, okay. Okay, here. All right. For now, without going being technical, if you can write starting with 3 functions, Q series, E2.
Oh, thank you. So everything generated by E2, E4, and E6.
Exactly. You are allowed to use integer powers of them to make monomials, and you can have complex coefficients if you like.
Yeah, thank you. You already had the slide. Sorry. Thank you.
Yes. Yeah. Sorry, I didn't have enough time to expand. Okay, so now a number of authors worked on Ramanujan's claim, and in this couple of papers with several authors, they were able to prove Ramanujan's claim theoretically using what Ramanujan gave as derivatives of the Eisenstein series. As you can see, the Eisenstein series E2, E4, E6 are closed under derivative. And these identities they used to prove Ramanujan claim. And then George Andrews and Bruce Byrne in their book, they wrote, they expanded on this one, discussed, but nowhere can we find any explicit formula for the quasi-modular form expansion. So, and in fact, in the title of this slide, the title of this slide is what they wrote in one of the papers. They found it to be a little bit difficult to do. All right, to continue on, in fact, to answer Andrews and Byrne, let's introduce something. Given an integer in frequency, given a partition in frequency notation, as you can see, we introduce with Ono and Singh, we introduce something called partition Eisenstein series. This is a mapping from partitions to a product of Eisenstein series. You're allowed to use E2 up to N. Notice that things double at the bottom index on the Eisenstein because you only have even index Eisenstein here, if you want to talk about quasi-modular forms. And the multiplicities in the partition are reflected in the exponent of the Eisenstein series. So we call E lambda partition Eisenstein series of weight to N. Then we define a weight to N Eisenstein trace. What does it mean? If you can find a set of coefficients for the E lambdas, the partition Eisenstein series, and the coefficients depend on partition of all partition of N, this sum is what we call trace, Eisenstein trace. It's a weight to N, exactly weight to N. It's a pure weight. So this construction depends on nothing but the partition function that you can come up with, phi. P here is the set of partitions. For example, if your partition function, if your mapping phi that depends on lambda is purely constant, and lambda n is equal to 3, there are 3 partitions, this is what the trace looks like. For example, if your function phi is counting the number of parts of a partition, then obviously you get E6 twice E2, E4, and then 3 times E2 cubed. All right, what did we move on to next? In this work with Ono and Singh, we were able to express the Ramanujan functions as traces of Eisenstein, trace of Eisenstein series, both of them, of course, with different phi function. And these are the expressions, explicit expressions using Bernoulli numbers. These are the partition functions that go into the trace, and this settles the question of Andrews and Bernd because we have found the coefficients. And next, you don't have to remember, but there is one thing we would like to say about the bottom phi function. It will be before I do that, let me write an example. These are just the examples again with partitions of 3, and these are the mappings, the phi functions. In the first case, U function, these are the coefficients, and then we were able to get Ramanujan U6. And if you do t equal to 4, then you're going to get these things. These are the coefficients. One thing you like to observe here is the second one, the V function, which is now expressed as the trace, is desirable for combinatorialists for sure, compared to the first one, because they're integers. These are integers. So in fact, before I proceed, just to indicate what do we need to do to prove this, we need the concept of Polya's theory of cycle index polynomials. I probably will not go in detail, but that's the tool, really important tool that plays the role of proving this result that I just finished mentioning. And if you like, you can package all of the cycle index polynomials with parameter t in this exponential generating function formulation. So that is about the proof. Okay, now one thing we'd like to mention, this is work with Barman and Singh, a recent paper. This is a desirable result. Why? Because the U's on the left, the script U on the left, are MacMahon's functions, but the U's on the right in red are Ramanujan's functions. So it means that we were able to connect the two, MacMahon and Ramanujan. And the connection is not random. The connection is after finding the coefficients W, then it's telling you that actually the MacMahon are quasi-modular of weight, mixed weight up to weight 2t. That means you can have weight 2t, weight 2t minus 2, and weight 2, weight 2, weight 4, weight 6, and so on. But what this statement tells you is that the pure weights are exactly Ramanujans. Okay. All right. Now going back to addressing explicit formula for Ramanujan U and Ramanujan V. This is work with Ono and Singh. Here we were able to find the coefficients. When you write something in the partition trace formula, then we have found coefficients, but please don't forget, in that expansion, all Eisenstein series are involved. U2, U4, U6, U8, blah, blah. But in here, we're being minimalist. We only use E2, E4, E6 as Ramanujan desired. But these are the coefficients. I don't expect you to remember, but I'll say the other one. V2T has a similar description and explicit formulas which are defined recursively. I don't write initial conditions just to minimize the notational amount. This is work with Barman and Singh. Okay, now there is something I will add in connection with Ramanujan, and that is if we have a partition lambda, let's say it's a partition of n, then in the frequency notation given, you might remember this. These are the phi functions given while trying to expand the Ramanujan v functions as a quasi-modular form, as quasi-modular forms. And this, I mentioned earlier that these are integers. So these whets our appetite as combinatorialists because we want to see what their interpretation. Notice here, for a good reason, I put absolute value to make them positive so that we are doing positive numbers. We don't want to deal with negative expressions. So then the first thing is these are integers. We were able to prove this. And then furthermore, if you add them all over the integers, over the partitions of the integer n, you get Euler numbers. And Euler numbers are famous and they have different interpretation. One interpretation is they count the number of zigzag permutations of 2n letters, zigzag or alternating permutations. So what this statement says, the second part, says is that we have found a refinement of Euler numbers because you can break them up into many pieces. But the question is, what do they represent? What do they count? The phi absolute value. This is work in progress, considering other stuff with John and Richard. And here I'll say briefly that U2n is the partitions and the permutations, zigzag permutations. And then there is something we define that we call record partition of the permutation. If that record partition of the permutation with some twist, W hat, if that quantity is a partition lambda, then that belongs to the set. And this phi counts all of such record partitions whose value is lambda.
Can you repeat again what you mean by a zigzag permutation, please?
Zigzag permutation means the first part is more than the second less than the third, and they alternate in size. They alternate in size. The first one is bigger than the second one is less than the third, and so on.
They're also called up-down permutations sometimes.
Up and down, thank you. Up and down permutations, zigzag.
And sometimes they're called Andre permutations, I think, because Andre is something.
Okay, thank you.
Okay, thanks, Doran, too. Thanks for asking as well.
But that's amazing. I have a quick question. This new parameter, RP, does it make sense for any permutation, only for up-down permutations?
You can define it for any permutation, but in this case, you can define it, but you need to tweak it because maybe I should mention, you could, but in this case, just to make a little bit sense out of this, the record partition of the permutation we computed, we don't use the W permutation itself. We do every even term.
Ah, okay. Thank you.
Yeah. Good question. Yeah. All right. So now, now we switch to something else, and there is a concept, or due to
Let me interrupt. That Zeilberger was a Rutgers PhD alumni.
Oh,
Sarasian, I think, went to Rutgers, PhD at Rutgers.
oh, is that okay? Small world. All right. And Dyson introduced ranks and cranks. I don't expect you to remember this in a minute. So, but let's say there are concepts called cranks and ranks, which are absolutely instrumental to make to give explanation to Ramanujan's famous three congruences, and let's call them C lambda. And now, in this case, in our discussion for now, what we need is moments of moments of cranks in the following way. First, you call M N to be the number of partitions of N whose crank is M. Just to remind, a crank could be positive, negative, or zero. So if you do cranks, count partitions by cranks, and then you multiply by to make a weight, a moment, m to the power of d, d's moment, obviously. And then the generating function, you write this way. We were not the first to write this, other people did. But we were able to write these moments as trace formulas, in a convolution of trace formulas with Dedekind eta function hanging on the right-hand side. Okay, fine. This is a partition function associated here. All right, what I want to mention is the following. These generators, the C generators of the D moments, were actually considered by Atkins and Garvan. They were able to express them, at least inductively, without explicit coefficients, in terms of the Lambert series given here. The right-hand side is just the divisor. The phi function is a generating function for powers of sum of divisors that we have been talking about. Then they were able to they proved that inductively these generating functions are polynomials in these quantities without explicit coefficients. All I have to say now is, with Michael Griffin, Ken Ono, and Singh recently, we prove actually that the explicit formulas come from partition Eisenstein, except we don't use the Eisenstein series E, because that's not what Atkin and Garvan did. So they want it in terms of phi, we got it in terms of phi. By the way, phi and Eisenstein are closely related. One is missing constant terms, leading constant terms. All right, and on the last, in the last few minutes, we'll switch gears to some invariants in topology. Cobordism topology. And the first one is called the A genus of spin manifolds. We don't need to know this technical terminologies and so on and so forth. I'm not an expert myself, but these are given by these expressions that don't look intimidating at all. And they were able to express these invariants in terms of what they call Pontryagin classes, the E1, the E2, the E3, and so on and so forth. And there are infinitely many of them. What's the connection with what we do? First, we put them in a generating function format, and we look for others. There is another genus for closed smooth-oriented manifolds, the L genus, and this is given with a similar structure using Pontryagin classes. And what do? We put them in generating function format. All right, now here is what we are going to express. Earlier, if you remember, we use Eisenstein series E, but with a different normalization for the purpose, for the current purpose, we had to switch to G, a different normalization. You just pull out the Bernoullis and rewrite differently. That's all it is. But this formulation is better for us. And then once again, we construct the partition Eisenstein trace. Mind you, the only difference is here is G, earlier it was E. Using those, we're able to express these two genera, Hirzebruch genera and the A genus, as traces of partition Eisenstein series with a G, not an E. And explicit formula for the partition functions given this way. This is work with Griffin and Ono. Okay, now in all cases that we have been considering, things can be summarized by proclaiming that in the particular case of genera, as well as the things we discussed due to MacMahon and also Ramanujan, there are one way or the other Jacobi forms for those number theorists at heart. Okay, now just to make one thing before closing down, and that is Ramanujan earlier introduced the U functions and the V functions, in particular the U functions. This was way back when, before the advent of this genera discussed. And he wrote the U functions. Now, as you remember, we can express them. You can express them in terms of the trace. This time using the E trace. Okay, E trace. And then if you do the same with the A genera, not the Hirzebruch genera, but the A genera, then the only difference is that the first one has phi, the bottom one has absolute of V, absolute of phi. That means take absolute value of the partition function. Okay, therefore, actually, those functions, those quotient of theta functions, the U's, actually anticipate the genera expressions. I think I said this, but here is an explicit formula for phi once more. And just to compare for visual aid.
In what sense he anticipated? Obviously, he didn't know about this fancy Hirzebruch classes and topology. So, in what sense?
That means what amuses me is this is probably a subjective judgment when I say anticipate, when we say anticipate. But by this we mean it's amazing how these things are omnipresent, these U functions.
Or how they grow up, right? Yeah.
Yeah, and although I will not get a chance to get there, these U functions in a recent work with Ono and a colleague from Haifa, Leonid Fell, these things appear also in complete intersection numerical semigroups. The same functions from Q series from Ramanujan.
So that's beautiful. The unity of mathematics, it's really beautiful.
Yes, yes. So we couldn't resist to call it anticipation. So these are examples, just in case you want to compare Ramanujan U with the A genus. The only difference, as you can see, is in the sign of the numbers. And of course, there is an extra universal multiplier of A3. That's why the denominators differ. Otherwise, in the numerators, everything is clean, it's the same. How does one recognize over the other as far as decision of signs is the number of parts. If the number of parts, as you can see in E6, is 1, then it's negative. If you have 2 parts, the sign does not change. In the last one, there are 3 parts, so therefore it's odd number of parts, so that it becomes a change of sign. And finally, this is the last slide. If we limit ourselves to the modified or renormalized Eisenstein series, G4, G6, G8, and so on and so forth, then this become modular. These are modular forms. G2 is the odd man out. That's not modular. Then this actually gave rise to the Witten genus. And on the other hand, there is something missing. There is a piece missing here in this sum, the red sum, k equal to 1, that goes back to G2, the quasi-modular forms. But if you take the G2 star completion of that and include it in here, then it gives you, it connects you or becomes an avatar for the A genus that we discussed earlier. Well, like all good things, this too has come to an end.
Thank you so much for very, very intimidating but beautiful talk. It's amazing how the unity of mathematics, also different things from MacMahon, Ramanujan, and Hilterbucher, Witten. This, if I didn't know you so well, I would have called you a name dropper. But I'm sure it's a very, very deep connections between the various parts of mathematics. And I was really pleased to see my favorite Polya index theorem, which is a tool of counting in combinatorics, but it's nice you can use it for other things. Other questions for Tewodros, for Telly?
Before you ask, let me give credit. The very first paper we wrote is responsible for what you have seen today. That was worked with George Andros and Roberto Taurasso. At the end, after we finished that paper, George said the following, I quote, he says, "This is gonna catch fire." And it did.
Yeah. So it was
these are papers only that we humbly did, but many other papers came out of this, including papers like prime. This was due to Ken and colleagues that are prime detecting polynomials out of MacMahon.
Wow. Yeah. Well, it's really nice how MacMahon and Ramanujan show up again in very, very recent deep stuff. That's very. A question for Telly? So how did you learn all this fancy stuff? I didn't teach you all this. So you learn on the job. Wow.
Well, Doron, it's all about the initial conditions.
Yeah, right.
You give initial conditions and then the rest was routine.
Okay. But I really like the experimental aspect. That so it's really nice how the abstract and the concrete come together now. And all these existent things before, now you had explicit ways of expressing them in terms of the Eisenstein series. That's really. More questions?
Hi. Maybe I have a.
Oh, go ahead, Stan. Nice to see you.
Yeah.
Hi.
Hi, Teddy. Maybe just say a few words about this combinatorial interpretation that is work in progress. What is this quantity, this new parameter? What is its definition?
Okay. Are you talking about this slide?
Yeah.
Are you talking about this slide?
Yes, this one with this RP.
Record partition. It takes a little bit of time to explain it. It's a construction in the following sense. You take up and down permutations on two n letters, and then we single out, let's say, the even parts, the even index parts. If you have permutation pi 1, pi 2, pi 3, up to pi 2n, you take pi 2, pi 4, pi 6, and so on, okay? So that's what we call here omega hat. Once you have omega hat, what you do now is you look for, in this sequence, new sequence of n letters only, you look for left to right maxima.
Okay. Yeah, the
And then, yeah, if you get a left to right maxima, you record it. And then you do that until the end of n. And then after you put them together, then they may not be in order, monotonic order. So rearrange them. No, sorry. I should say before that. Once you have done that, then let's suppose the new sequence you have found is A1, A2, A3, A4, okay? What you do now is you do successive difference, A2 minus A1, A4, A3 minus A2, and so on. Surely they are always positive because you're doing left to right maxima. Once you have listed them, the new sequence, let's call them B1, B2, B3, blah, blah. Those numbers may not be in decreasing order. So you're allowed to rewrite them, rearrange them in decreasing order. When after you finish doing that, you call that a partition.
Right.
You call it record partition.
I see.
Does it make sense?
Yeah. So okay, this phi of a lambda is the number of those zigzag permutations with that record. Okay.
That's right. By the way, as a side note, here I mentioned some of the absolute of phi over partitions of n is Euler, but notice, my friends, look, the one I put in red in the top formula, the 4 to the k, 4k minus 1, blah, blah, with absolute value of Bernoulli divided by 2k, these are integers, and they are the odd index Euler numbers.
And by the way, look at the chat. Michael Somos has a question about this.
Yes, yes.
Look at the chat.
Oh, okay. I think I need to close it down. All right.
I'll read you. In the combinatorial interpretation, the quantity in red.
Yes, I think what he's asking is the one I just mentioned in red. He's asking, are they integers? Yes, they are integers. They are the odd indexed Somos, the odd indexed Euler numbers.
So the problems are yes.
Definitely.
Yeah.
Definitely.
Interesting how everything connects.
Yes. Stoyan, did I answer your question?
Yes. Thanks. Thank you.
Okay. Thanks again, Teddy, for such a very, very fascinating talk. And the slides, please email me the slide when you have a chance. And the recording will be available. We'll let you know. There's no talk next Thursday, but the next seminar is in 2 weeks. So see you all in 2 weeks. And thanks for everything. Thanks for coming. Bye-bye.
Thank you so much. Thanks so much.
Thank you. Aurora, please end this meeting. Bye-bye.